during the pandemic, she did a lot of that and helped us along with some mini lessons and much, much more. So you can follow her on Facebook at Starla Creative Teaching Tips or on YouTube, Starla Ewan. Take it away, Miss Starla.
All right. Hi, everybody. So tell me, I see you guys there. Hi. Yes, I want to see you. And you can unmute, ask questions, because this is really kind of a Q&A review. I can't predict. First of all, in 3 hours, I couldn't go through the whole topics of everything you need to know. We did do this one time in person and we filmed it. And I know that's a resource for you. But also I know as you go through here, you know, it's been a while since you've looked at some of this stuff and now you're going to be tested on it. So I just thought I'm going to hit each area. I'm going to ask if there's any problems. And then, you know, any questions, you just pop in and go, yeah, could you go over da-da-da-da-da? And I will make it as simple and as easy to understand so that when they give you that Q&A, you're good. Okay. All right. So the first, of course, thing that we've got here is the foundations of science inquiry. Boring. I'm not even going to lie to you. This is the boring part of biology and anatomy. I see y'all laughing, but it's true. It's a true story. So what I like for you to do is, are there any questions about the fact of, first of all, scientific method? All right. They're going to ask you questions about scientific method. When you read through the steps of scientific method, a lot of times, you know, you just read through it and you get, okay. But then they're just going to ask you questions or scenarios. So I like to use the light bulb, okay, as just a simple way to reinforce scientific method. Okay. Are there any questions about it? All right. So give me an example. Here we go. Ready? You walk into a room and you turn the light switch on and the light doesn't work. Now, being the humans that we are, we click it on and off and on and off and on and off and on and off, right? Isn't that funny that we do that? But what we're actually doing is our brain is gathering data. And that's the first thing. The first part of the scientific method is, one, we got a problem. Light doesn't work. Then we begin to gather information. I'm not sure what information we're gathering, if it makes us feel better to open and close that little switch. But for some reason, now we're going to come up with a hypothesis. All a hypothesis is, everybody's just an educated guess. It's just a hunch. What do you think, based on what you've just gathered, is the hypothesis? What do you think? What do you think, Linda? What do you think, Brooke?
The light bulb is burnt out.
Okay, that's our hypothesis. So now we have to test it. All right, so Linda, do you have a different hypothesis? Do you think the light bulb's burned out?
The light switch may be off.
Maybe the light switch, but we've clicked that on and off. Maybe there is something wrong with the light switch. Okay. Anybody else got a different hypothesis?
Electricity's off.
Electricity could be off. Good. Anything else?
Phone breaker.
Oh yeah. Breaker. Is there anything else out in the room? That's gathering information and data. Maybe the light bulb is just loose. Okay, so we've got these hypotheses. Every single one of those, now we need to test it. Well, what's the easiest one to test first?
Change the light bulb.
Change the light bulb.
Change light bulb.
Yeah. Or go
Flip the switch.
tighten it up. Tighten it up, see, oh, it's already tight. Okay, all right. Then we go change the light bulb. All right. If the light bulb comes on, boom, what do we got? Solution. That's it. Not a problem. Our hypothesis was correct. We changed the light bulb. By turning the light bulb on, that is our experiment. Okay. In an experiment, we have what we call the solid. That's what works every time. And then our variable, of course, is the light was out. Okay, so that worked. Or it could be we turn it on and it still doesn't work. So somebody said the breaker. So now we're going to go back. So do you see one thing about textbooks are really poor about teaching on the scientific method is they teach it linear. You know, you start and you gather data, you come up with a hypothesis, you do an experiment, you gather information, and does the information support your hypothesis? Right? Everybody familiar with that? But what are we doing? We're coming here, we have a problem, we're gathering data, we're testing our hypothesis, and then what do? We go back. You see? So I want you to understand that the scientific method isn't really truly linear. It's more where it cycles back. Okay, does that make sense? So you get an idea. Okay, well, now our light doesn't work. So somebody said breaker. So we go to the breaker. And being humans, always remember that we are interesting characters. We see the breaker is on. There's nothing wrong with the breaker. But what do you think we will do anyway?
Turn it off, turn it back on.
You betcha. You got it. We're going to turn it off and turn it right back on. And maybe not just one time, maybe a couple.
For all of them. Mhm.
Exactly. Okay. Then we run back and we have a new light bulb. We flip the breaker. We turn it on. Nothing happens again. Okay. Still got our problem. Gather more information. What could we look for now?
Something in the wiring.
Like maybe is it plugged in?
Yeah.
You know, that whole on off switch? Yeah. So we go and we go look. And sure enough, the lamp is not plugged in. There was our problem. Yeah. See? Okay. So I love to use that scenario. And when you teach this, if you teach it in your classroom, it's part of your curriculum. It's a great scenario because do you see how many variables can be with just having a light out in the room? And it's simple, students can relate to it. And it also shows them how the scientific method is not linear. It actually is a continual loop. And a lot of times in research, just say I'm researching, a particular type of melanoma. This happens in research all the time. You're thinking you're linear, but then you start testing a variable, and next thing you know, you've got 3 or 4 variables starting to line up, and you end up looping quite a bit. That's how great discoveries are made. Okay, you were testing for one thing, and next thing you know, you got 20 different variables that are happening. So that's the neat thing to show students is that a lot of times when we do scientific method, keep it simple with like a light bulb, or you can also use another example of the car not starting. Okay, that's another example. And I love us as humans. What do? We sit there and try to start it over and over. What are we doing? We're gathering data. Okay, then we're starting to run a hypothesis. Is it the battery? Is the battery dead? And then I love this part. We go and we open the hood and we look at it. Now, how many of you know anything about engines? Well, probably about 3 of us out of 25 know anything about engines. The rest of us just staring at it. We just think, gosh, if I just stare at it, maybe it'll work. By bringing out human character into the scientific method, it also keeps it from being so dry and boring, but also the same kind of thing happens in a research lab, the curiosity of humans, the researcher, questions. That's what research, that's the magic of research. Okay, so you can use those simple scenarios to show them. And for you also understand when you're answering questions about that, remember, yeah, it's listed as linear, but what happens if your experiment did not support your hypothesis? You were wrong. No big deal. We take the information we gathered from our, quote, failed experiment and create a new hypothesis from it. And it loops. Does that help? Okay. All right. So looking at the first thing you have to do, any questions about that? Help you? Is that a little more lively? Okay. All right. So I'm just looking through here. And okay. So history of some of the sciences. Any questions on that? DNA, microscope, you all know that's a little more factual information, correct? Okay. The discovery of DNA, be careful with that. I'm not sure how they're doing the questions. I looked a little bit at some of the sample tests and I didn't really see anything that was too alarming. But the history of DNA is kind of like a lot of science discoveries where several people did research, but they weren't talking to each other. And here you got Watson and Crick, and they go and they take all the pieces and they put it together and they get the gold medal for discovering the structure of DNA. Just keep in mind, they truly didn't do all the work. They just sat back and they saw the forest. And they saw this group of trees and this group of trees and this group of trees, and they brought it together and they, boom, they discovered DNA. So kind of keep that in mind, the history of that, okay? That's kind of, you know, just factual stuff, nothing really to make exciting on that. Okay, everybody know your equipment? They'll throw pictures at you on equipment. Everybody okay on that? Titration, all that. Any questions on that part? Safety. Okay, now I know it don't make a big deal in that first part about safety, but one of the biggest parts of that first standard, okay, standard 1 there that they're covering, make sure you know safety. Make sure you know the rules. All right, now what's interesting about that is if you go and you look at the resources given to you or you Google lab safety rules, almost every set is different. Okay. All right, here's rule number 1 in safety. Read the safety rules. I know they'll say, what is the most important safety rule? Read the safety rules. That's the rule number 1, okay? I know you laugh, but it's a true story, okay? And then, you know, make sure you know where sharp objects are supposed to be disposed of. Make sure you know how to handle a fire. Make sure you go through those procedures if they fire 1 or 2 questions. Only 17% of your exam, okay? Is there a list of equipment that may be on? Yeah, you can even Google that. You can even Google it. All right. You can even find even some biology exams, like just a chapter 1 biology exam. You can look at that and you'll see there's pictures of equipment and then you match them up. But do make sure you know a burette, titration, a graduated cylinder. Make sure you can do that. They'll throw 1 or 2 questions at you on equipment. But I think they will also throw questions about safety on there. How do you dispose of broken glass? How do you handle a fire, etc. All right. Based
Hey,
on
Starla,
yes, ma'am.
what about the pictorial of the different hazardous materials?
Okay.
Will that come up?
You know, they change it every year. I've not seen it. They might ask, you know how they do that little triangle with the 3 numbers in it? That might be something they ask. Okay. And so you might want to know that. What is an acid? How is an acid labeled? Where would you store an acid? What kind of container would you store an acid in? And the reason why I'm spending time, I'm going to try to hit everyone in 3 hours, but I already know your background because you're in career tech. A lot of you are pretty solid in cell and in body systems, in which we're not going to ignore. But the heaviest questions are that will get you is kind of in this number 1 right here, because you kind of skim through it. It's boring, but they can ask you a question and put something up there and you're like, I have no idea what that piece of equipment is. And then boom, you miss a question. So I don't want you to ignore that first part. Okay. And then a lot of questions, I'll be honest, right now, the way the standard's been in this kind of test, a lot's going to be in genetic, and we'll get to that. It's always there. Okay. Well, we'll get to that. Not a problem. We got plenty of time for that. Okay. So yes, read over safety. And like I said, the sources that you were given are pretty good, but also you can Google a lot of that. You know, just Google in, how is an acid label and hit images and boom, you'll see that. How do you store an acid? How do you handle an acid spill? Those are the kind of things that they can throw at you. Okay. Now, let's be honest, in our classrooms, especially in health science, how many of us are going to handle an acid? Yeah. Okay. And I don't know about you, in Texas, we're not handling any blood products because we're not allowed to, unless it's that artificial blood, you know, not even allowed to do the spit lab anymore for digestion to show enzyme work. So you don't have to worry about that kind of stuff, more about just simple scientific stuff. And again, a lot of you are going to go, well, I'm never even going to do that in my classroom. They don't care. This is kind of a blanket exam, and you have to get through it. Okay. All right. So definitely go through that right here on that. What is it? Saparia? Is that how y'all doing? Is that called that unit 1? Make sure you go through it and hit every one and make sure that you can, you know, and just Google it and you can find all kinds of examples for it. Okay. Like they'll ask you, what is the difference between a hypothesis and a theory? Okay. Anybody want to answer that? Linda, you want to go for it? What's the difference between a hypothesis and a theory?
The hypothesis is the educated guess. And the theory is going to be something that someone's either tested or come with.
Yeah, over and over and over. Yeah. We don't want to call it a fact, but it's a theory because it's been proven, not just by you and by Brooke and by Susie and by me. We won't call it a fact, but we'll call it a theory because it's been proven over and over again. Make sense? Okay. All right. Okay. So any questions about unit 1? Dig in. Do take time to prepare that part for the exam. Okay. Because I find that when you guys take this exam, this is the one where we stub our toe the most. And again, it's just because it's not attention grabbing. Okay. All right. Any questions? Okay, good. Let's go on to the second part, cell structure and function. All right. So, all right. So let's talk about bonds. All right. It's been a while, huh, guys? All right. And and a lot of you in health science, we don't teach bonding. Okay. We only teach, you know, in anatomy, we sometimes do, sometimes we leave it out and we hope they've had chemistry, you know, and even if they've had chemistry, that doesn't mean they got it. Okay. All right. So I'm going to just throw a few little kind of tricks at you so you can remember. Okay. All right. So for example, here. Okay. And you can put this on paper too. So you have these examples. This is a hands-on kind of interactive. Okay. All right. So let's do ionic bond. Okay. Let's just do it really quick. First of all, the first thing we need to go through and just remind you of is remember what the atomic number stands for. Does everybody remember that? I know it's okay. You can shake your head and go, oh my God, I have cobwebs on that part of my neurons. Okay. So let's just do something really simple here. Okay.
Is an atomic number the number of protons?
And you're right.
It'd be the number of protons in the nucleus. An atomic mass would be protons plus neutrons, right?
One more thing. You almost have it. You got 95% of it. Come on, girl. You got this.
I'll take the 95% today.
Okay, watch this. Ready? Okay, let's just take hydrogen. Okay, everybody good? We got hydrogen. All right, atomic number 1. All right, she's correct in saying that that stands that it has one proton and possibly one neutron. Depends on if it's an isotope. Okay, so it's got one proton and one neutron. But that number also tells you, if you remember, protons are positive. PP. Protons are positive. Out here is going to be an electron. Because if you have one positive, you got to have one negative. So now you know the other 5%. So the atomic number, yes, will say it tells you the number of protons. That tells you what club it belongs to. If I have one proton, I belong to the hydrogen club, which is called an element. I know chemistry teachers fall over when I teach this because they're just like, that's kind of like, you're making it so simple. Well, yeah, because a lot of chemistry teachers make it too hard, too difficult. Okay, logic, use logic here. You got one positive, you got to have what? One negative. Therefore, I have no charge. See that? I got no charge. Okay, now watch this, everybody. Ready? See this electron out here? The electron determines the personality of this atom. It does. Okay. Now, you remember how logical, when we studied the human body, how logical it seems? Those of you in health science, right? I mean, the intelligence of the body is just cool. The intelligence of an atom is cool too. Okay. It's just the way it was taught to. It's like, okay, I'm with you. Okay, ready? All right. In order for a hydrogen or any atom to be happy, watch this. See this guy right here? He's zooming around the proton. Okay. Now, it's interesting. Sometimes we call these electrons shells, clouds, orbitals. There's so many names. There's like 3 or 4 names for them, but whatever it is, it's the space in which the electron travels around the nucleus. And it is so fast, of course, you can't see it with a visible eye. Okay, is everybody good? All right, and I love to ask you guys, have you ever seen electrons? Yes, you have. You've seen lightning, and that's electrons. You've shocked your spouse. That is an electron jump. Okay, I'm going to explain how that works. Okay, first of all, here's the personality. I'm making a dot right here in the middle of my page. That's the nucleus. It doesn't make any difference what atom it belongs to. Okay, all right, ready? Just remember this. In the first shell, cloud, electron orbital, remember the number 2. It can only hold 2 electrons. That's as many as it can hold. All right, from now on, remember the magic number 8. Okay, from now on. All right, so in the second orbital, we've got 8 electrons. See? Now, when you get to the third, it'll say 16, and then it says second level, third level. Who cares? Okay. Just remember, what is 16 divided by 8? 2. It's 2 levels. So the third level has 2 levels, but we don't care about that. We just know from now on, everything is what? Everybody good? That's easy. How simple was that? So in the first layer here, we have 2. From now on, it's what magic number?
8.
8. That's it. Okay. Everybody good? All right. Super. Okay. Ready? So here is the bottom line to an atom's personality. First, it is either happy or it is unhappy. There's no in between. Okay. It is happy when its outer shell is completely full or completely empty. That is what makes a happy atom, either completely full or completely empty. That sets up its personality. That's going to tell you what it's going to want to do. All right, everybody okay? Good. Let's go to hydrogen. Happy, unhappy. Unhappy. That's right. Because it has one electron out here, but he wants what?
2.
Perfect. Good. So here we go. Ready? So if I take a hydrogen and I get him next to another hydrogen, they can do something.
Share
can-
electrons.
They can share them. That's right. Now, I said I was going to do ionic first, but I ended up going to covalent. Ready? Here we go. Ready? 1 proton, 1 proton. So you got 2 protons and you got 1 electron, 1 electron. And what are they doing?
Sharing it.
They're sharing them, and they're sharing them equally. They got married. Yeah. It's not a strong bond because they're only sharing 1 electron. Okay. So when they share electrons, it's called covalent. All right. So we're just going to do that. And then we're going to go to ionic, and then we'll come back to covalent. So does everybody see I shared it? Both are happy. They end up with 2 electrons because they're sharing it. Okay. This is how we write it. Because we're sharing 1 electron, we put 1 bar between them. See right here? That 1 bar tells us, 1, they are sharing the electron. The second thing it tells us is it's a covalent bond right there. Okay. All right. Is everybody good? Okay. Now let's jump a little bit. Ready? Okay. So the first thing we want to do is fill shells. Okay. So I'm going to jump now to a different bonding, and then I'll come back to covalent. Okay. So here we go. I'm going to take sodium. Okay. All right. Everybody look up sodium and tell me what the atomic number is. Use your phone, whatever. Okay. All right. What's my number?
11.
11. Okay. All right. Here we go. All right. So I'm putting a line underneath it, and I've got 2 electrons in the first shell. All right. 11 minus 2 is what?
9.
9. Okay. What's the next shell? What can the next shell hold?
8.
8.
8. So let's fill it. Okay. So I filled the second shell. All right. How many electrons do I have left? 1. Here we go. 1 electron. I've got 1 electron going around the very outer shell. Is sodium happy or is sodium unhappy?
Unhappy.
Unhappy. What does sodium want to do? What's the fastest way to become happy?
Give away that 1 electron.
Give it away. I don't want to share it. I just want to get rid of it. All right. All I got to do now is find somebody who wants an electron. Okay. So let's look up chlorine, everybody. All right. What's the, all right. So chloride, what's the atomic number on it?
17.
17. Exactly. Okay. Fill your shells. Fill them up and I'll put it up there. It's been a long time since you guys did this, huh? You're like, where were you when I took chemistry? I know. I felt the same way when I was in chemistry. Okay, so this is what I have. 2, 8, and 7. Is that what you have?
Mhm.
Perfect, good. What does chlorine want?
1 electron.
One
It
electron.
wants 1 electron. It doesn't want to share it. It wants it. Okay, so watch what's going to happen. Sodium is like, you betcha, here you go. Sodium is going to give, it's giving it away. Here you go, hands it over.
Can you talk me through the chloride?
Uh-huh,
I'm sorry, the chlorine, how you got the 8 to 7 again?
you betcha, you betcha. That's what I want y'all to do. I want y'all to ask questions, okay? All right,
Because
so
I just wanted to say, so if I take 17 and subtract it from 2, right?
well, you're gonna fill the shell. So the first shell gets 2.
2,
The second shell, now that we've got 15, we've got 17 minus 2, we got 15 left. The second shell is gonna get 8.
right?
Good. And
Yeah.
now I've got 7 left.
Gotcha. Okay,
Yeah.
thank you.
Okay, you're welcome. All right, so this guy right here doesn't want this guy. He's got this 1 electron just zooming around here. You don't want him. He's like, he's a pain. I don't want him. This guy wants 8. So think of atoms as having personalities. Okay, all right, here we go. Boom, gives it up. Okay, now, ready? Down below here. Sodium still has 11 protons, right, everybody? It never gives up its protons. If it does, then what happens is it changes it's no longer sodium. Okay. All right. We've got 11 positives. How many electrons do we have after we give it away?
10.
10. All right. So we've got 11 positives and 10 electrons. So sodium is going to take on a positive charge. See that? See why? That's the question. So I'm one of those students where, I didn't do well when the teacher just told me this is how it is, because I'm the why kid. Why? So that's why I want you to always go, why does it have a positive charge? Because it gave away an electron. All right, so now sodium has this positive charge. All right, tell me about chlorine. What happened to it?
So it would have 17 protons and it gained 1 electrons, which would make it a negative element.
Bingo, it's negative. That's right, because it took on an extra electron, it now has a negative charge. They're not sharing. This was a giveaway. Okay, what do you know about magnets, positive and negatives?
They attract.
Bingo. And so what do you think these 2 atoms are going to do?
Attract each other.
That's right. And they're just dating, everybody. They're not sharing. They're not married. They're just dating. They're only together because one has a positive charge and the other has a negative, which means they're easy to break up. It's easy to break them up. Okay, is everybody okay so far? Okay, good. Ready? When an atom gives away or takes on an electron, it becomes an ion. An ion is an atom with a charge.
Can you repeat that for me, please? I'm
Sure
sorry.
can. You bet. No, don't ever be sorry. Pop in as much. Okay. This whole session is for you guys. Okay. So yeah, ask as much as you want. Okay. When an atom takes on a positive or a negative charge, it's called an ion.
So that makes it an ionic bond.
You got it. So when they hook up like this and they date, this is ionic bonding. All that means is two or more atoms are hanging out together just because of charge. That's it. So salt, if you put it in water, what happens to it?
Dissolves.
That's right. They break up, don't they? Because they're just dating. They're only held together because of a charge. Our bodies are not made out of ionic bonding. We would fall apart in the ring. Does that make sense? Yeah. Okay, I'm going to go back real quick because I can tell I feel the brains filling up as we do this, okay? And it's okay, guys. I want you to understand it's all good. It's been a long time since you've seen this. And more than likely, a lot of times is explained in a way that just seems, it just didn't make sense. Okay, ready? Let's keep it simple. What makes an atom happy?
Full or empty shell.
That's it. Either you got a full shell or you got an empty. That's it, period. That's all its goal is. Okay. That's what determines its personality. Now, if I got one electron out here I don't want, and I find another atom I can give it to, I'm going to. When that happens, I end up with more protons than electrons, and I take on a negative charge. Is everybody good? Okay. If I accept an electron, I have more electrons than protons, so now I take on a positive charge. If we're near each other, we date, which is ionic bonding. All right, now one more piece of information. Each of these has a specific name, okay? If I'm a positive ion, I am called a cation ion. Now I'm going to show you how you can remember that, because the T makes a positive. So you can always remember that cations are positive. I don't know if they'll throw that question at you or not, but I wouldn't be shocked by it. That's your trick, okay? If it's a negative ion, it's called an anion. This is how you can remember it. Ready? A negative ion. Y'all see the trick? So anion is a negative ion. All right, now, ready? It's funny that in chemistry and physical science and physics, we call these, of course, ions and cations and anions. But in medicine, in the human body system, we refer to these as electrolytes. It's the same thing. Electrolytes are ions. So think about it. At a cell membrane, we have the sodium-potassium pump, right? Kicks out 3 sodiums and pulls in 2 potassiums. Well, both of them are positive ions to set up the resting membrane potential. So once again, you see where you have chemistry and physical science, and then you have human body systems, and they don't talk to each other, but you're talking about the same thing. Okay. All right. So let's do calcium real quick. All right. All right. Look up calcium.
$20.
All right, 20. Let's do it. Okay, we got 20. Okay, fill your shells. Tell me what you end up with.
Is it 2?
Yeah, you got 2 out there floating around. All right. Okay. So I'm just going to double check you. You should have 2 in the first shell, 8 in the second shell. Okay. 8 in the third shell and 2 in the outer shell. And you betcha he's going to want to give those away. So calcium's going to give those away. It doesn't matter who he gives them away to, but he's going to give it away. So now tell me, what's his charge going to be?
Positive.
How many?
+2.
2. That's right. So you'll see a lot of times in a textbook, you'll either see calcium, whoop, 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 there you go, with 2+, or you see it written this way. Okay. All right. When you look at that, what does that tell you? What did that atom do?
Wants to give it away.
It gave it away. It gave away 2 electrons, and I have a double positive charge. That is how calcium is in the human body. Okay, in body systems. Well, not just human, but all animals. That's right. Yeah. So, man, it's quick. It's quick to give it away. It may give it to hydrogen, it just gives them away. So when we talk about calcium in the body, it always is in the form of this electrolyte. Okay. Does that help everybody? All right. So that's as simple as we want to keep. Well, that is ionic bonding. That's it. That's how simple it is. Okay. I know you keep waiting for the shoe to drop, but that's it. Okay. Now let's go back up to covalent. All right. When we did the 2 hydrogens side by side, do simple math. We have 2 positives, we have 2 negatives. This is a great marriage. It's equal. They're happy. Okay. There's no charge, nothing. Okay. Everybody feel good about that? All right. Look up carbon. What number we got carbon?
6.
How much?
6.
6. That's correct. Okay. All right. Here we go. We got, there's carbon for us. All right. Okay. Fill them what you got. What's in your outer shell?
4.
4.
4. Oh, that's a dilemma. That's a dilemma. What do? We're not happy.
So we find something that can give us 2. Give us 4.
Okay. Let's put him up. Why don't we put him next to another carbon?
They share it.
And how many?
4.
Okay, so how would you draw that?
You link them together so that each circle touches each circle.
So you would make 1, 2, 3, 4. 4 electrons. See, so every dash represents a covalent bond in which we're going to share 4 electrons. Notice in ionic bonding, we do not use the lines. Only in covalent bonding. Does that help? So just when you read a question on there, if it talks about salt or sodium chloride, you know that's ionic bonding because there's no lines. Okay. If they show you a molecule that shares lines, you know it's what?
Covalent bond.
Okay, now we're sharing 4. Now watch this. That means I've got 12 total positives, and I've got 12 total electrons. Just like the hydrogen, the positives equal the negatives. Everybody good? All right. So this, once again, is equal sharing. Okay, now we're going to come back and give it a name in just a minute. All right, now drop down here on your paper, probably about 5 lines. Okay. And let's do oxygen. All right, look up oxygen. What number is it?
2.
Well, what's its atomic number?
8.
8. There you go. Okay. All right. You're right. What's it going to share? It's got 2 and then 6. What's it want? Because I know that's what you jump to. It wants 2, doesn't it? Okay. Now, even though I can't see all your faces at once, I just want you to know this. If you're sitting there going, I think I'm catching on, but I'm not sure. Say something. All right. Okay. This guy's unhappy. He needs 2 or wants 2. He doesn't want to give his 6 up. He's willing to share. Who is easily happy to share? Let's see here. Let's try these guys. Who are they?
Hydrogen.
Ah, and what do hydrogen want to share? Just 1, right?
One electron.
Okay, so let's do it. If each one of these hydrogens will share with this oxygen, the oxygen will be happy. This guy will throw them up there every once in a while. Now, but watch what happens. How many positives do we have up here? Yeah, how many positives do we have down here? Okay, so this is like being in a restaurant and a couple walks in. And one of them, I'm sorry, they're beautiful. They're eye candy. Like phenomenal. And the other one is cute. You know, just like me, just kind of cute. Okay, yeah. Just through normal human behavior, who do you spend more of your time looking at? The phenomenal, cute, beautiful one. All right, good. Because you're more attracted to that. Don't lie. Okay. Even though they might be ugly on the inside, we're just looking on the outside. Ready? Watch this. If you're an electron and there's 6 positives down here and only 1 up here, only 1 up here, who you gonna spend more time around? All right, so watch what happens. Here we go. I'm an electron. See what's happening? I spend more time rotating around 6 positives, and then I'll make a circle up here to keep hydrogen happy, to keep him there. But I don't spend as much time up here as I do down here. Is this a good marriage? Is this good sharing? It's unequal, isn't it? Okay. Now, so that means in this molecule, in this covalent bonding, electrons spend way more time around the oxygen than they do the hydrogen. That means these guys are naked a lot of times up here. So I have 6 positives, but I end up mainly a lot of times with 8 electrons down here. So this part of the molecule gets a negative charge. Do you see why? And these guys are naked a lot of the times. So what charge do they have? That means that this molecule has a positive charge on one end and a negative charge on the other. even though it's still covalent, it's just unequal sharing. And by the unequal sharing creates poles, a positive pole and a negative pole. Also kind of looks like a cute polar bear with his little ears. See it? So this is called polar covalent. Polar covalent means because of the unequal sharing, it creates poles, a positive pole and a negative pole. You guys know who this molecule is?
Water.
That's right. It's water. It's H2O. All right. So in covalent bonding, this molecule is written as H2O. 2 hydrogens, 1 oxygen. Does water love itself? Very much. Yes. So watch what happens. Okay. It's the great endless doodle. Okay. So write this first. Just make a small version of it. Okay. Now, if I have another water molecule, how would it line up to it?
The oxygen on the other molecule attaches to the hydrogens on the other. on the
That's
front.
right. Yeah, you bet. So it'd go like this. See? And you could add another. It's the endless doodle. See it? You can just keep adding it. So wherever there's a hydrogen, now here's the catch. That's not a very strong attraction. So these guys look like square dancers. They hook up and then they let go, hook up and let go, hook up and let go. And you know this as a liquid. If I add heat to this, the energy from the heat will make these guys go so fast, they'll separate. The heat will lift them up. And you know that as a gas, as vapor. Or I could pull heat and energy, molecular energy away from them, slow them down, and then freeze them in place. And you know that is ice. And ice freezes the molecules where they actually did their last handshake or square dance move. I can't look at square dancers and not think of water molecules. It's true. You know, they're just moving around doing this. That's exactly what water molecules are doing. They're just bumping into each other, attracting these positive to negative, but they're just moving around, constantly moving around. How fast they move around depends on what the temperature is in the environment. So look at a cloud. Okay, especially a cumulonimbus, a thunderstorm. All right. All right, so the bottom of it becomes dark, correct? That's where the water is cooling. Then as the heat from the ground comes up, it causes those molecules to move faster, so they become vapor and they rise up to the very top of the cloud. You see it boiling up, right, everybody? And when it does that, then it's going to cool and it's going to drop down and cool off and release more energy. And then this is what's going on inside a cloud like this. See it? See it turning? And all that is water molecules going up. They run out of energy. They fall back down. And eventually, if they cool enough, then they fall to the ground. If they get up high enough, they freeze. And once they freeze, then they gain energy from gravity, and they may thaw out and then rotate again. Or what happens? They hit the ground as hail. Okay. So water right here is attracted just kind of by this positive and negative right here. Is everybody cool? Okay, now watch this. Any molecule that is a polar covalent bonding is going to be hydrophilic. Okay, so any molecule that is a polar covalent has the same personality is going to be hydrophilic. Philic means love. Okay, so you're driving your car in a rainstorm, the rain's hitting your windshield, and then the wind's blowing it, and you see the water dancing along your windshield to the side or down the sides of the window, right? Okay, so here's what's happening. This water molecule right here, the wind's blowing it, and what's he doing? He's grabbing the hands of the other ones and pulling them along, and then that one's pulling that one along, and this one's pulling this along. Yeah, and you all know that as capillary pull. Yeah, it's pulling it along. Now, why does the water hug the glass? Because the glass is, guess what? Hydrophilic. So if we go and give blood and they take that little tiny needle and punch our finger, what do they put up next to it? A little capillary tube, right? Everybody, a really thin glass tube. And what does our blood do? It just climbs up it. Yeah, because majority of blood is water, and water loves glass because they're both hydrophilic, and zoom, it just shoots right up it. That's cool, huh? Okay, now I'm gonna throw some biology at you because I don't know how much of the kingdoms they'll throw at you, but I know they throw some questions at you, okay? In the plant kingdom, okay? In the plant kingdom, you have two kinds of plants. You've got non-vascular plants, which means they just absorb everything directly in direct contact with moisture, okay? And then you have vascular plants, okay? Vascular plants are really cool. Now, when you guys go out and water your trees and bushes and flowers, tell me, where do you water? Where do you place the water? Do you shoot it up at the leaves?
At the
Or do you
base.
at the base? Okay. How in the world does it get up to the leaves?
It's absorbed by the roots and the roots carry it to the top.
You're close. You're right. The roots are going to absorb it because they have these little tiny root hairs. They're a lot like capillary tubes. Inside the root is a straw. There's a straw. Now, like if I gave you guys like 6 straws and I put a glass of water across the room and you connected the straws and you put it into the glass, and you would have to suck on it. But once you got it started, you could drink that whole glass of water, couldn't you? Ah, okay. So that little straw, like tissue, is just like, boom, 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 and it goes into the stem.
So it
And then-
siphons it.
Do what?
It siphons it.
Pretty much, but it's using capillary pull. That's that tissue that straw is made out of pulls the water up. It's capillary pull, and it'll just keep pulling it up into the branches and then into the leaves. And you see in the leaves, you see veins, don't you? Those little vein patterns. Yeah, that's that tissue that started in the roots. Okay, you ready for the name of that tissue? You're gonna love it. Don't be afraid. It's called xylem. Okay, now here's how you can remember it. Xi up to the sky. It only travels one way. Xi up to the sky. And guess what? Xylem is hydrophilic. So it has capillary pull. So when you go out today or tomorrow and you water your plants or your trees, use your Superman glasses, put them on, see through the soil and see the little root hairs pulling the water out of the soil. going into the xylem, all the way up the trunk, into the branches, and into the leaves, spreading out those veins and filling those cells full of water. Isn't that cool? Yeah, you're seeing it right before your eyes. Capillary pool. You see it when you have rain, which we all go outside and dance when we get rain. And you see that water dance on the windows because the glass is hydrophilic. Xylem is hydrophilic. And let me tell you how you know that. See the paper you're writing on? This is xylem. How about that? Y'all remember learning how to count the rings on a tree to see how old it was? That's xylem. The wood of a tree is xylem. Makes up the majority of the tree. Cool, huh? Yeah. So when we make paper, it's made out of xylem. Ever spill water on your paper? What'd it do? It got all wrinkly because it absorbed the water. Doesn't matter how fast you get it off of it. Yeah. The only thing, I don't know, those cheap paper towels we put in school systems, I'm not exactly sure what that's made out of, but I don't think there's a whole lot of xylem in them. They just float across the water. Yeah. The only thing I found it's great for them is to take clay off your hands when we build out of clay. All right. How's everybody feel? Good? Yes? All right. Okay. So hang on real quick. Okay. Based on what we know about brain-based research, okay, it is time for you to stand up, stretch, and we're going to take a quick 5-minute because this is such a short time, but I know to keep going, I'm just going to look like the Peanuts teacher, blah, 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 and it's not going to go in. Okay. So everybody get your phones up really quick. And I want you to set your timer. Okay. And you set it for 4 minutes. I'll set mine for 5. At 4, whatever you're doing, quit and come back. But get up, walk around, stretch, pee, get you a drink of water, but do something. On your mark, get set, go. See you in 5 minutes. And you can use those YouTube videos in your classroom. It's under my copyright, but you have permission to share with students. So, you know, look through, there's a couple biology ones in there too, you know. Okay, so starting where we were at, I was trying to tie in with this hydrophilic molecule, which is a polar covalent bond. Any molecule that is polar covalent is hydrophilic. Okay, now we want to tie in one more tissue that you may see on the exam because I'm trying to pull in kingdoms as we're doing the molecular stuff, just to show you that, you know, instead of just learning it like a lot of students learn, okay, it's a polar covalent, but then that's where it stops. We want to carry it on so you guys can carry it through the test. Okay. All right. So here we go. So, you know, xylem is a straw-like tissue that carries water up in a plant. And of course, it does capillary pull. It's hydrophilic. Okay, now, what happens in the leaves of the plant? Anybody know?
What do you mean what happens in the leaves of the plant?
Yeah, what happens? What's the purpose of a leaf?
To grow.
Okay, it makes something, you say. It makes something.
Photosynthesis.
Oh, bingo, photosynthesis. Okay, all right. So, does anybody know what we need for photosynthesis?
Sunlight.
Sunlight and chlorophyll.
All right, so chlorophyll is a lot like the hood of your car or a solar panel on your house. Its job, of course, is to capture energy, and it's really cool. It's got these green discs, okay? And the discs are like little solar panels, and they absorb the sunlight. And when they get full, then they rotate down and then another one comes up. And their job is to capture the sunlight energy. And then it takes carbon dioxide and water. Okay, so where'd the water come from? The roots, right, everybody? Because you watered it. All right, carbon dioxide, it brought in through these little tiny pores called stomata. There's little tiny pores underneath the leaf, okay? It brings it in, and then what it does is it takes carbon dioxide, water, and that energy, and it locks that energy because it creates these guys to come together, and you know it as glucose. It makes glucose. It gets 6 carbons, 12 hydrogens, and 6 oxygens locked in, and it locks that sun's energy into that molecule because it takes energy to make a molecule, and that's glucose. That's the purpose of a leaf. Okay, now, the cells in the leaf will use some of that glucose. Hey, does the branch need some glucose? How about the stem, the trunk? Hey, how about those roots? Do those roots need some glucose? They've got to have energy in order to grow, right? To do mitosis. So when the leaf takes sun's energy and forces carbon dioxide and water to form glucose, then the food, okay, travels down. It's going to travel down from the leaf, the stem, into the roots along this tissue called phloem. Let me spell that right for you guys. Okay. All right. So phloem. Oh my gosh, I'm having a brain fart. Here we go. So phloem, okay, P-H-O-L-E-M, phloem, there you go. Phloem, it sounds like what?
Phlegm.
Yeah. I love my health science people. It flows.
Flows.
That's right. And water flows where? Downward. Okay. So phloem usually carries the food down the plant, but it's being used. But it can also go up. So watch what's happening. Right now we've entered fall. And as the daylight gets shorter, the chloroplast will begin to die out, and you'll see other pigments, yellow pigments, and you know, the keratins and the pretty reds. But what's happening is the energy, the food is flowing down the stem and into the roots where it'll be stored for winter. You still need to water your plants during the winter, but maybe once a month. Okay, everybody good? Especially before a big freeze. That's always helpful to them. In the spring, the branches need food to make leaves, so the phloem will go where? Back up to have energy for the branches to make new leaves. But once the new leaves start making energy, the phloem will carry food where? Downward and feed the organism. Okay, so I'm pulling in plant stuff with what we're talking about, because a lot of times in a 3-hour or even a 2-day, we never get to plants, and plants are so cool. Okay. All right. So any tissue, the 2 plant tissues that we're going to probably throw at you. Xylem goes where? And carries what?
Water.
Water. Ready? Phloem carries
Food.
food. There you
Glucose.
go. So phloem carries food and usually flows which direction?
Down.
Downward. But in the spring, it goes where?
Up.
There you go. So do you guys like syrup on your pancakes?
Yes.
Good. So on special trees like maple or pecan, we can tap into the phloem, and as the sap or the food flows down, we can tap it, let it drain out, and what do you have?
Maple syrup.
There you go. You're eating the phloem, the tree's food. How cool is that? You had no idea that this tutorial was going to change your life. You know why you water trees at the bottom, and now you understand, you know, the tissue flow of the tree. Isn't that cool?
Now I feel bad for eating the tree's food.
It's okay. They make plenty.
Okay.
All right. Here's another thing. All right. So on a tree, these two tissues, okay, these two tissues, when they're alive, okay, they're found in the bark. Okay, so I'm going to draw this really quick for you. All right, so you guys learned this when you were in elementary, right? To count the rings of the tree. All right, so now what you've learned, this is all xylem, right, everybody? But watch this. This is dead xylem, and it's known as the wood of the tree. Therefore, this would be a woody tree. Hence, get it? It's got wood. Okay, all right, I know. I'm telling you, scientists are so brilliant by stating the obvious. Okay, then this part right here, I'm going to darken for you. It's pretty thin, actually. Could be about 1/4 to 1/2 inch thin. See this outside? That's what you know as the bark of the tree. All right, so the bark of the tree has xylem on the inside, and then it has a mitotic ring, and then it has phloem on the outside. So you have xylem, a mitotic ring, and then phloem, and then you have this cork barrier, which you guys refer to as the bark. Here's what's neat. This is the living part of the tree. The bark is the living part of the tree. Now, the outside of the bark is a lot like your skin. You know how it kind of puts a dead layer out on the outside of it? Yeah. But underneath it, it's very alive. So have you seen people carve into a tree before? That's very damaging to a tree. Very damaging. Because you're cutting through the living tissue of the tree and you're causing a wound. Sometimes they'll sap out with it, okay? But what they'll try to do is it'll try to heal that wound. You'll see it eventually go away. All right, now, let's say you go and you buy $300 trees. You've got 6 of them right, along your, maybe between your property line, between you and your neighbor. You're putting up a wind block or maybe a neighbor block. You may not like them very much. Who knows? Okay. All right. So ready? So you hire this company to do your yard while you're out of town. They take a weed eater and they go around, cut that high grass around your tree. Unfortunately, you know what they also do? They take the bark right off your tree with the weed eater, because on a brand new tree, the bark is, I don't know, maybe 1/4 inch thick. You come back and all your trees are dead, or they start dying. You're like, what do they do? Yeah, they girthed your tree. They took the bark all the way off. When that happens, well, one, food can't go where? Down to feed the roots. It's called girthing a tree. Lots of people do that and not even realize what they've done. So I want you to understand that the bark is where the living tissue of the tree is, which is the xylem and the phloem and of course the cork. Okay. So you had no idea. We take a molecule, we learn about plants. Okay. The other term you may hear in plants is herbaceous. That's a non-woody. Okay. That would be like asparagus and the plants that you made, like verbena, the plants, moss rose, stuff you plant in your garden, vegetables, those have a green stem and those are called herbaceous. All right. Now, some of those guys can transfer food to their roots and they'll come back again next year, kind of like hibiscus does. All right. And those are called perennials because peri means many. Or like verbena, and you put, verbena and geraniums and you pack up got these beautiful plants in your planters. But once winter comes and they freeze, what? They're gone. So those are called annuals. So an annual means it only lives for one season. And perennial means it'll come back year after year. Why? How does it do that? It puts food down into the roots. And then in the spring, it will begin to use its energy to put new sprouts up and leaves, etc. Okay. You good on that? Okay, good. We got some plants in there. Okay, now, well, hopefully I can get some more in. Okay, let's go back to our polar covalent. Once again, remember, any molecule that's polar covalent is hydrophilic. Okay, so what's it called if I've got this guy right here and he's equal, to equal sharing? I've got 12 positives and 12 negatives. Everybody's sharing equally. Okay, well, that means there's no positive and there's no negative, so it's pretty much called non-polar covalent. Okay, so non-polar covalent means it's equal sharing. There's no poles. No poles. There's no poles. There's no positive, there's no negative. That means there's equal sharing. Okay, here's their personality, everybody. You're welcome, Patty. Hope we helped you. Okay, ready? Okay, so non-polar, watch their personality. They are hydrophobic. What's that tell you about their personality?
We're scared of water.
Yeah, they don't like it. They are not a fan and they will run. Okay, so let's put this guy up here. Every time I show this, students are going, it's a jellyfish. Well, in Oklahoma, they may not say that. Okay, it's got 3 fatty acid tails. This is a long, long chain of carbons, hydrogens. Okay. These are fatty acid tails. There's 3 of them, and this is a glycerol head. So this is glycerol, and these are fatty acid tails. You all know this in your blood work as a what? Triglyceride. That's right. There he is. He's a little jellyfish in your blood. Okay, let's talk about his personality. Ready? The tails are non-polar covalent. In the head, glycerol is polar covalent. Okay, what's it tell you about the personality of this triglyceride?
The head loves water and the tail is scared of water.
That's right. So part of the fat is hydrophilic. That's why I did a smiley face. And the tails are hydrophobic. You got a dual personality molecule here. Okay. All right. Watch this. I'm going to draw this jar here. Okay. Everybody draw you a little jar. It's okay. It's not Art 101. Make you 2 circles in a line. I like the EKG in the background. This is not, you make my heart flutter. Little VTAC on that. Okay, ready? So this is water. This is oil. There's water, and there's a layer of oil. Okay, why did it separate out that way?
Because oil is heavy, lighter than water.
Okay, that is true, but go back to this.
So then our oil would be non-polar.
Yeah, what are the tails trying to do?
Hydrophobic?
They're trying to get out, aren't they?
Yeah.
All right, so watch what it looks like. If we put on our Superman glasses, this is what it looks
So
like.
they're upside down.
That's right, they're upside down. That's right. So here's water. And there's the layer. Look, they're upside down, getting away from the water. Okay, then there's another layer. and they stack on top of each other because remember, hydrophilics want to be together and hydrophobics want to be together. So there's what your next layer looks like. Then what would your next layer look like?
The heads would be together.
The heads will be together. You got it. Perfect. Okay, so if you've ever been at a gas station during a rainstorm and you look down and you see gas that's been spilled and the water is picking it up and carrying it away, correct? Yeah. Okay, because the water gets underneath it and the heads go down. It's this oil, and then the tails go up and you get another layer and you layer. Okay, so if we've got a dry pavement with water and then this, and we haven't had rain in a while, and you stop, where's your tires at? Right
It skips
here.
on the surface of the water.
There you go. So you're sliding across the top of the water. You hydroplane, even though it was just a real light rain. That's why a lot of times when we haven't had rain in a while, then we get a rainstorm, there's wrecks everywhere because people forget you've got to give yourself time to let your tires get contact with the pavement under here. Otherwise, when you stop, you're just sliding across the oil on top of the water. Because as tires go across the pavement, they leave a residue. When it rains, that residue gets picked up. What's the residue made out of? A fatty substance. Cool? Okay, let's go back to this. Ready? Let's shake it up. We're gonna make a salad dressing, right? We're gonna shake or stir this up. We're gonna force the oil to go down into the water. When you look at it, what do you see in there when that happens?
Bubbles.
Bubbles. That's right. You see bubbles. This is what the bubbles look like. Three-dimensionally, I'm not drawing it too. You know, I'm leading to something really important, right, everybody? That's what the bubbles look like. See, where all the tails? They're on the inside. Where are all the glycerol heads, the hydrophilic heads?
On the outside.
Next to the water. Yeah, they're next to the water. These are called micelles. These little bubbles are called micelles. Those tails, they're going to find every way they possibly can not to be next to that water. They will not get next to the water. How about wax in your car? What's that look like? Metal is hydrophilic. So when you get wax poured onto your car, if you put on your Superman glasses, this is what it looks like microscopically. There's your car hood, and then there's a sheet on top of it with little heads, and the tails are floating in the wind. When they move around, they correct static electricity and you catch dust. Dust gets attracted to those tails. Fires you up after you get your car washed, get a nice wax on, you go out the next day and it's dusted. You're like, what? Yeah, well, that's why. But if water were to rain on it, what does the water do on the tails? It tries to tippy toe across the tails and it bubbles up and gets off your hood. Do y'all see this cool microscopic world of either loving water or hating water? Pretty cool. Okay, which brings us to the cell membrane. Now, the cell membrane, triglycerides, by the way, even though fat gets a really bad name, right, everybody? It's a terrible name. But your body has to have fat. It has to have at least 50 grams per day. Okay? We don't have to worry about that in the United States. We far, far surpass that. Okay? Here we go. So, when triglycerides are absorbed into the small intestines, of course, they're broken down and they're carried to the liver, of course, is going to take and it's going to break it, you see? It's going to break the tails off and it's going to begin to send some of it to the cell. It may send it to the cell as a triglyceride. It may pull the tails off. See them right here, they got yanked off. These are called free fatty acids. And this is what your heart uses for fuel. Your heart does not use glucose. It's one of the few organs in your body that does not depend on glucose. Aren't you glad? Because if your blood sugar dropped, what would happen to your heart rate? Yeah. Your heart, it's kind of ironic, isn't it? That it uses free fatty acids for fuel. Kind of has a love-hate relationship with. See this glycerin right here? Cells can use this for all kinds of stuff, like making earwax and synovial fluid and all kinds of neat stuff. Yeah. Okay, everybody good? Okay, so one of the things can happen when a triglyceride lands in the liver or at a cell is we can yank off one of those tails and add a phosphate to it, and we get this guy right here. See, he only has 2 tails. And you all know him as a phospholipid. All right, for a cell membrane, okay, I'm gonna go to a new page here. Everybody okay? Okay, all right. For a cell membrane, you all know a cell membrane is built how?
Tasha, you're muted.
So the phospholipid bilayer.
Bilayer, here we go. Why?
To allow some things in and some things not to come in.
Okay, what's on the outside of the cell?
Water.
Is there water on the outside? Okay, good. What's on the inside of the cell?
Water,
Okay, so why do we need a bilipid layer?
because we need the hydrophilic sides to be facing the water and the hydrophobic
Got
sides to be together.
That's right. So the interstitial fluid, or I'm going to shorten it up and call it matrix, okay, is water, and the cytoplasm is water. So you have to have a bilipid layer or a bilayer of phospholipids. So you have glycerin on the outside and fatty acid tails on the inside. It's dry in here. So again, remember when you're going through this stuff, and some of it it's been ages since you looked at, always ask the question, why? Why is it like that? Because remember, everything it's logical. It's got to make sense. Now, do you notice that we have not talked much about ionic bonding? Because basically ionic bonding just forms electrolytes in the body. Your body is primarily covalent bonding. And most of it is going to be covalent bonding with carbon, hydrogen and oxygen. That's pretty much what you're made out of. Okay. All right. Is everybody good? All right, good. Now, here's a neat thing. Not only is the cell membrane a double layer of phospholipids. Okay. So here we go. Here's my cell membrane. But so is the nucleus. It is also made out of a bilayer of phospholipids. So is the mitochondria and the ER, whether it's rough or smooth, the Golgi, lysosomes, a vacuole. In other words, just about every organelle inside the cell also has what, everybody?
A phospholipid bilayer.
Very good. So in cells, in our cells, they have, these are called membrane-bound organelles. Okay. And therefore, they are called eukaryotic cells. We're going to throw that at you. So eukaryotic cells have membrane-bound organelles. Okay. Now, remember this trick. Eukaryo. You rhymes with, okay, so you do have a nucleus. Karyo means nucleus. So eukaryotic means you have a nucleus. Everybody good? Which means you could be a protista, a one cell single organism. Or you could be, and all of you are fun gals and fun guys. Ha ha ha, get it? The fungi kingdom. Get it? Fun gals, fun guys. I love fungus. It's really cool. Thank God we have it. They're the decomposers. Okay. Or you could be part of the plantae kingdom, which we've talked about some today. Or you could become an Amelia. All right. So eukaryotic cells form these kingdoms. Because they have a true nucleus and membrane-bound organelles. Okay, so how's everybody with that? Everybody kind of good? Okay, all right. What happens if you just have this then? Okay, I'm gonna change it. You have a cell membrane. Okay, see just the cell membrane, but what do you not notice? There's no membrane bound organelles. Okay, you may have a little thing of genetic material that's shaped like a circle. You may have ribosomes in it. But as far as enzymes and metabolic activities, they're contained in the cytoplasm, but not in any membrane bound organelles. Okay, I'm putting on here. This is DNA. It's looped. Okay, because we do not have membrane bound organelles or a true nucleus, this is a prokaryotic cell. Pro rhymes with no. There's your trick. And I know for some of you that has been a long time ago, like freshman biology in college was probably the last time some of you guys saw that. All right, always remember this. The only organisms that are prokaryotic are bacteria. That's it. Yay! They're broken up into two kingdoms now. They used to be in one, now they're two kingdoms. The first kingdom is archaeobacteria, and the other one's just regular bacteria called Monera. Archaeobacteria means ancient bacteria. The archaeobacteria are able to live in very, very harsh environments, such as like volcanic water, like sulfuric water, high salt levels. Does that make sense? There's not a lot of them. And then the Monera is just the regular bacteria you get. Cool. Because their cytoskeleton is organized a little different, if they have a flagella, just remember it's a corkscrew. It moves like a corkscrew. It does this movement. If it does have a flagella, it's the way the cytoskeleton is set up in the arrangement of the proteins. So if it does this, you know it's a prokaryotic. Okay, eukaryotic flagellas are a 9-2 arrangement, and they do this. They do that sesamoid snake-like movement. Okay, does that help you set up your kingdoms? Okay, so there's 6 kingdoms, 2 of them prokaryotic, the rest are what? Eukaryotic. Perfect. Okay. All right. Okay. All right. So how's that help you with molecules? Good. So you understand ionic bonding, covalent bonding. Okay. And then of course they're wanting you to, let me pull this back up for you. Okay. So you got that comparative. All right. So because of covalent bonding, you can make huge molecules like carbohydrates, proteins, fats, which we talked about, DNA molecules. All right. RNA molecules. So that's that. Remember, they're all covalent. All right. Everybody good?
Can you repeat the two kingdoms that are in the prokaryotic family?
Archaeobacteria. It's ARCH, archaeobacteria, and then Monera, MONERA, Monera.
Thank you.
Okay, and you might want to Google it because I'm going to tell you something. I swear, I feel like they changed that Monera name a million times. I read just a minute. They have a committee meeting. They're like, let's name it this. Okay, so make sure it's current. But you know, you got two, because they used to have just one for bacteria, but just make sure. I know there's two right now. Okay. All right. Is everybody okay with the, okay, so carbohydrates, proteins, fats, DNA and RNA are known as macromolecules. Okay, is everybody good with that? Those are your macromolecules. Those are your molecules that you take in from another animal or from a plant or a fungus. Okay, like you, when you guys have mushrooms on your pizza, you're eating Basidio micata. Okay, just order that next time with Pizza Hut. Hey, I want a cheese pizza with some Basidio micata on it. Yes, okay, yeah. It has the protein chitin in it, which is a lot like biotin. Okay, all right. So your body takes that, your digestive system, which you already know, its job is to break this animal, plants, fungus, macromolecules, what made up that body of that organism, down into single macromolecules, which then you absorb. It goes to your liver. Your liver's your grocery store. At night, when you go to sleep, you need to sleep 7 to 8 hours. I know if you're in perimenopause or menopause, that could be a challenge. Okay. Your liver distributes these macromolecules that you took from the food you ate and distributes it and restocks your cells so that your cells can repair, grow, do mitosis, grow fingernails and hair. How about that? So you really are what you eat. Because DNA, which we're about to go into, DNA, guys, is DNA. It doesn't matter if it came from a fungus or from a tomato or from a buffalo, it's still DNA. And we break it down into little pieces called nucleotides. And you take that nucleotide, it goes to your cell, and now that nucleotide becomes your DNA. I know, just think what you're made out of, right? Okay, so one of the things we can talk about in fast foods, which could be some questions they ask you, is what's the problem with fast foods? What do they lack?
Nutrition.
That's right. And when we say that, they lack macronutrients. They lack the true tissues that animal or plant was made out of. They cooked it right out of it. So you're eating empty food. It fills your stomach, but it doesn't feed your body. It doesn't supply the body with any nutrients. Okay, so for example, I'll pick on McDonald's. I do it all the time anyway. It's not that they're the only ones that do this. If you're the biggest beef producer in the world, how do you prevent not having an E. coli outbreak when you've got all these animals on top of each other and you're feeding them food that isn't natural to their diet, which is what they feed them is corn. Cows do not, corn is not a natural part of their diet. And when you feed a cow corn, it makes a dangerous form of E. coli bacteria in its fecal material. If you feed a cow nothing but grass, it does not form that E. coli. It'll have E. coli just like you have E. coli, but it's not the dangerous form of E. coli. Okay, so how are you, if you are the largest meat producer in the world and you mass produce it and you feed them corn and you got them on top of each other in all these feedlots across the world, how do you keep from having an E. coli outbreak?
Antibiotics.
Yeah, they give them antibiotics. What would you do to the meat? You know, because they just grind the meat and it becomes piles of hamburger and the person's all wrapped up, you know, and they got their gloves and they take a scoop of the hamburger and they put it on the conveyor belt and it goes down the conveyor belt. How do you assure, I mean, you got bacteria all mixed into that. How do you assure there's no E. coli outbreak in Japan or Australia or the United States? How do you make sure of it?
Test it.
Treat the meat. Spray it. What's a good thing to spray it with? Ammonia. What's a great way to kill bacteria? Ammonia. So it goes through the little thing, makes it into a little hockey puck. We spray it with ammonia, flip it, spray it with ammonia, wash it, cook it, freeze it, put it on the truck. When you put ammonia on a protein, what's it do to the protein? It
Breaks
changes
it
the
down.
shape of, that's right. It changes. Like you're like, therefore, it's right. It breaks it down. It changes the shape of the protein. It denatures it. And therefore, yeah, it's safe to eat it, but what's the nutritional value of that burger? Yeah. In fact, it's tasteless. If you take all the sauce and everything off of it, it's tasteless. Try this. Go buy and get you a little hamburger from there. Go to find a friendly ant bed, a red ant bed, and take it and just lay that hamburger out and come back in a week and see how much of it's left. The burger will still be there. Those ants won't take it downstairs. If ants, because they're like, I don't know what this is. Yeah, yeah. Scary, huh? My rule is if fungus won't grow on it or an ant won't eat it, I'm not touching it. Okay. All right, the 6 macromolecules. Oh, they're ready. Carbohydrates, proteins, fats, DNA, and RNA. There's only 5. Micromolecules, the micromolecules. Yes, that's right. Grass-fed all the way. That's right. Now, watch out for this, though. Like if you go to Sprouts and it says grass-fed, but you notice the color of it is much like the other. That means it came from another country. So if it comes from England or another country and it's grass-fed, but they finished them off with corn, they can still call it grass-fed. Beware. Always look at the color. The color of a grass-fed beef is darker. It's a dark look. Yeah. Okay. So, and that once again, we're not, that's right. We are not protected by, you've got to, and of course, you know, Americans we're busy. We don't have time to go and educate ourselves. Okay. But even though we're a little off topic off your thing, that's things, these are great topics to bring into your classroom because you can help educate your students. You got to eat. So you might as well eat something that fuels your body and not just fills your stomach. Okay. All right. So I wanted to talk about those. Is everybody okay with like transport through the cell membrane, like diffusion, facilitated diffusion, osmosis? Everybody okay with that? Remember active transport. Ready? A, active, trans, T, port, P, ATP. So active transport uses ATP. That's your trick. ATP doesn't stand for active transport. It stands for adenosine triphosphate. Okay, it's an energy molecule. But You can help students remember, and you can remember. Active transport uses cellular energy to pull something from a low amount, a low concentration, to a high concentration. You're forcing molecules to go where they don't want to go. That would be like you asking me to go to the mall 3 days before Christmas. Why don't I want to go to the mall?
Too many people.
Oh, it's, yeah, so you're trying to force me from the comfort of my home, which is a low concentration, to a high concentration. I do not want to go. You have to bribe me. It's going to be a good dinner and a good dessert for you to get me to go. You don't have to force me to go. Okay, everybody good? All right, look at my time here. Woo, okay. All right, so let's try to get to 3 here. Let's get to genetics. Woohoo! Okay. Let me show you something fun here. All right, you all familiar with DNA? Yes. Okay, so get your hands out like this. Make me an L. I know in West Texas here in Lubbock, that's guns up for Texas Tech. Not here for us. It means DNA. These are nucleotides. Okay, Punnett square. You got it, Karen. We can do it. Ready? Here's the Punnett square. All right, so here we go. Here's a nucleotide. Now flip it the other way. So DNA has half a ladder going up and the other half of the ladder going down. This is a hydrogen bond right here. That's 2 hydrogens sharing 1 electron. You remember him right here? Okay, so that's what holds the DNA ladder together. All right, which means just sharing 1 electron is pretty easy to do what to it? Pop it apart. Yeah, it's really easy to pop it apart. We can pop the DNA ladder apart for 2 reasons. 1, in interphase. Y'all remember interphase? Remember doing the cell cycle? Okay, do it with me. Here we go. Get your hands up like this. This is interphase. Okay, this is when the cell is actually just doing its job. You know, it's making things, doing whatever it's supposed to do, absorbing, whatever it's supposed to do. Ready? Either it begins to age out or it gets too big for itself. It gets triggered and knows it needs to divide. So when it does that, right now it's in what's called G1. All right. It goes into S. S is DNA replication. Pretty simple. If I'm going to split this guy in 2 and I have 46 ladders because I'm a human, I got to make a copy and make another 46 ladders. So I'm going to do that in S. That's DNA replication. It's pretty simple. We just pop this guy open. We take the DNA nucleotides that you got from that tomato and that okra and that steer or that chicken, whatever it is, and it's going to come in here and match up and make 2 identical ladders. Everybody okay with that? So we unzip it, we match it up, and we end up with 2 identical ladders. Everybody good? So we went from 46 chromosomes to 92. Okay, good? Okay, now let's see. I need a rubber band real quick here. Let's see my desk if I've got a rubber band. All right, when we take a break, I'll go get one and I'll come back to this part. Okay, ready? All right. So interphase, everybody good? The reason why we do this is you really can't see the DNA. It looks like a fried egg. All right, the cell looks like a fried egg. You can see the nucleus, can't see the DNA because it's the DNA is stringy and it's in chromatid because we can pop it open and read it. Okay, so then in S phase, we start copying these ladders. All right, now we go to G2. Now G2, if I'm going to split this cell in half, I got to give everybody mitochondria. I got to give everybody rough ER. I got to copy the organelles. Everybody see the process? This takes a lot of energy on the cell part. Okay, and it takes macromolecules. So you got to have good nutrition to do this. All right, so here we are. That's interphase. Everybody good? Now we're ready for mitosis. Mitosis is the equal division of the DNA molecules. Okay, that's all it is. Mitosis is the equal division of the DNA molecule. So here we go. Y'all know this. So we've got 92 ladders. We're going to supercoil them, and I'll do that after our little break. We're going to supercoil them into tightly coiled DNA molecules called chromosomes. They're supercoiled to make them short so we can move them around. Everybody cool? All right, so here's ready. Everybody look up. First phase of mitosis, do this. We're supercoiling the DNA molecules. This is prophase. There we go. Then they're going to line up in the middle. Got 92 chromosomes, 46 on this side, 46 on this side, all lined up in the middle. This is metaphase. Meta means middle. Okay. Now we're going to split them. The spindle fibers are going to pull them apart, and boom. 46 chromosomes going this way, 46 chromosomes going this way. This is anaphase. They look like two spiders fighting, or a spider sitting on top of a mirror. All right, they move, and they clump up. 46 chromosomes, 46 chromosomes. This is telophase. All right, everybody good? Okay, mitosis is over. We equally divided the DNA, but the cell hasn't finished dividing. We got to divide up the organelles and the cytoplasm. And so when that happens, pull them apart like that, pull them apart. That's cytokinesis. Cytokinesis, we divide it, we get two identical daughter cells, which automatically go into what? Interphase. They start doing their job. This could take 2 hours. It could take 7. They could be in interphase for months, weeks. If it's a skin cell, probably maybe like 5, 6, 7 days. Inside of your mouth, maybe 3. All right, does that make sense? All right, let's do it again really quick. Ready? So you can sit there and go through that so you make sure you have it. So interphase is not part of mitosis. This is when the cell is just doing its job. It's living. It's in G1. Okay, then it knows it needs to divide, so it copies its DNA. So that's S. Then we copy our organelles. We get ready to divide. That's G2. Now we go into mitosis. Prophase, supercoil those ladders. Metaphase, line them up in the middle. Split them equally. Anaphase. Telophase. Boom. Cytokinesis. Interphase. There you go, because it's a cell cycle. It keeps cycling. All right. Everybody feel good about that? Okay, so ready? Get your timers. We're going to take a quick 5-minute break. I'm going to show you when I come back the difference between chromatin and chromosomes. And then I'm going to show you, we're going to run through protein synthesis real quick. And then we're going to do some, you guys talked about genetics, and I know that's a big one. We'll spend that last hours. Okay, can you do that one time? I sure can. Ready? So here's interphase. Okay, and you do the 3 stages. G1, doing its job. S, copying DNA. G2 is where you're copying the chromosome, copying the organelles, getting ready to divide. Now we go into mitosis. Supercoil the DNA ladders into chromosomes. Metaphase, line them up. Anaphase, pull them apart. Telophase, you got 2 sets of 46. Split the cell, cytokinesis, back into interphase. All right, okay, set your timer. Everybody, I want you to, again, this is brain-based research, and I'm, one of these times when I get to see you again, you're welcome. When I get to see you again and we do some teaching techniques, this is another thing you want to realize when you're delivering lessons, that there's only so much their brain can take in. You got to give them a quick break. Okay. All right. So real quick here, I'm setting mine for 5. You do yours for 4. Get out of that chair. Okay. And also think of questions you know you want to cover. All right. All right. You guys ready? On your mark, get set, punch a clock. See you in 5. All right. Here we go. All right. So watch this rubber band. Okay. So this is the DNA molecule. See how it has 2 strands? But we know that the DNA molecule is in a helix. Everybody see that? Remember, one strand's going up, the other strand's going down. During G1, when we're talking about a cell doing its job, one of the things cells do a lot of is they make proteins. They do protein synthesis. So what happens a lot of times when we are teaching this, or it's been taught to us, they teach us mitosis, and then they teach us protein synthesis, but they don't ever teach us when all this happens and why it happens, okay? So an interphase when we say a cell is doing its job, well, that's where we do protein synthesis. Okay. Now, as a resource to you for the cellular stuff, on on STAR's notes on my website, okay, the module 1, which has body themes and the cell, I take you through all this step by step, and not only can it help you for the test, but it can also help you if you have to instruct this in your classroom. And it's been a while. Okay, and it can give you all kinds of, the rubber band and all this cool tricks, the hand motions, all that's in there for you. Okay, it's all copyrighted. You can use it in your classroom. Okay, all right. So watch this. We're in G1. We're in interphase G1. Now look at this. Look at my DNA molecule. You see? Now watch. Did you see it pop open? I know that was crazy, wasn't it? Look at that. Boop. Okay, so the DNA are in thin strands. That's why you can't really see them very well in the nucleus. All right, that's why it looks like a fried egg. That's called chromatin, T-I-N, chromatin. Chromatin is functional DNA. Okay, watch what it means. Ready? Because we don't have time to get through all the steps, but I'll just kind of walk you through it. Ready? Here we go. Each section of a DNA ladder codes for a specific protein. Now keep in mind, I'm about to take you through genetics. Look where this relates. So for example, let's say that this is the genetic ladder chromosome number 7. Okay, everybody see what I did? Okay. And it has sections on it. I'm making this really simple. All right, so one's dark, this is open, this is dark, this is kind of lighter, open. So each section of this DNA ladder codes for one protein. And I usually do this in color, but since we're doing it together, I'm just showing you. Okay. Now keep in mind, when we go into genetics and the Punnett square, this is going to tie in. This is where a lot of times instructors in biology do not tie in. They don't keep the flow going. It's too choppy. Okay, so everybody see right here? Okay, so this is chromosome number 7, and each one of these sections codes for one type of protein. Therefore, you know it as a gene. See? Now, the reason why I said this was number 7 is because there's another chromosome number 7. They hang out together. Okay, so what do you notice about number 7 and number 7 about the gene pattern? They're the same, aren't they? Okay, that's important because one of these came from mom and one of these came from dad. All right, so when we lead into genetics, keep in mind to form a brand new cell that has 46 chromosomes, you got 23 of them from mom and 23 from dad. When the sperm fertilizes the egg, the number 7 from the dad, from the sperm, goes and finds number 7 from the mom, and they pair up. How do they know each other? Well, look, see, they match up. This gene right here codes for a specific protein. Let's say it's part of the hair color group. It isn't just one pair of genes for hair color, okay? But one protein. That piece of the genetic ladder is called a gene. Okay, so watch this. Here we are in interphase. Your hair grows constantly. So ready? An enzyme from RNA, ready? Watch this. This is in G1. Boop, pops open the gene. See it popped open? Popped it open. RNA, messenger RNA, will go copy just one side of it. Because DNA is the blueprint of the cell. We don't let it go anywhere. It has to stay in the nucleus. If you were building your dream home, everyone, if you're building your dream home, would you take the original blueprints to the site in which it's being constructed, or would you take a copy? All RNA does is make a copy of that gene and then leaves the nucleus and then takes it to the protein factory, which is the ribosome. And the ribosome will read that template 3 bases at a time and put a string of amino acids together to make this protein that this instructions tell it to make. How'd you like that for protein synthesis? Pretty easy, huh? Yeah. That protein, once it's made, is put inside the rough ER, and all the ER, endoplasmic reticulum, is a subway, and it's going to transport that protein. And because everything's membrane bound, it's going to put it in a little taxi called the vesicle. Then that vesicle is going to go over there and attach to the Golgi. The Golgi will package it and either ship it to someplace inside the cell. We might have made something for the cell itself, maybe to repair another organelle, maybe to repair part of a cell membrane. You know how furniture jumps out and gets you sometime. Don't you hate that? I hate it when it does that. Or it might be, in this case, we're making hair, so it will produce it and place it outside, and it may be part of the follicle shaft, and we add that protein to the bottom of that and take it up. See how it all makes sense? So you don't always have to, it doesn't have to be chopped up. So this is DNA, chromatin. It's functional. We can pop it open, read it, make the protein, and then close it back up. Now, let's be honest. Let's think about it. If I go to all that trouble to make a template to copy that gene, do you really think I'm just going to run it through one set of ribosomes and make one protein? Or should I run it through several sets? Yeah, I'm going to run it through a bunch of ribosomes and make a bunch of proteins. Yeah, it doesn't just go and do one thing. It's kind of like coronary bypass surgery. We don't crack somebody's chest open to do one bypass. We're going to do at least 3, 4, 5, 6. You know, we're not going to do one. Okay, is everybody cool? Okay, so now in interphase, we know in G1, we have chromatid. We're doing our job because we're popping open the DNA and copying it. Okay, now S is when we're doing what to this ladder? Yeah, we're making copies of it. So once again, we pop it open and we're gonna, these are called replication bubbles, and we're gonna replicate this DNA ladder. Okay, here we go. Prophase. What are we doing in prophase? We're supercoiling, right? Okay, watch this. Here we go. The DNA ladder is twisting and twisting and twisting. It's supercoiling. I don't know if y'all remember that movie Superstar. The kids don't anymore, but I love that. I'm like, supercoil. Yeah, they're looking at me like, she smokes crack. I know it. Like, never in the morning. Look at that. Y'all see that? I supercoiled the rubber band. Look at that DNA ladder crawling back on itself. Do you see it? That's a chromosome. The chromosome supercoils, so it becomes really knotted up and short, so I can move it around the cell now for pro, meta, ana, and telophase. See? Question. Can I make a protein? Can I read this DNA ladder? I can't open it up. It's supercoiled tight. The only purpose of a chromosome is for mitosis or meiosis, just for cell division. That's the only time we form chromosomes, because it's not functional. Look, guys, I can't open it. It's so supercoiled tight, I can't read the DNA. The only purpose of a chromosome is to move it around in the cell for metaphase, anaphase, telophase. Okay, after cytokinesis, what does this sucker do? It uncoils. Okay, it uncoils, and now we're back into interphase where it's now functional and I can pop it open and use it again. So the difference between chromatin is functional DNA. Chromosomes are formed, they're supercoiled, so we can move them around during cell division. Okay, is everybody good? Yay. Okay, here we go, genetics. Whew. You know, there's never enough time, is there, Susie? Never enough time. All right, so let's say this set right here is in the egg. Well, get ready to form the egg. Okay, now in girls, the eggs are formed before birth. So meiosis, or what is known as oogenesis. All right, that is because the egg's true scientific name is a oocyte. I know, you just want to kick the scientists, don't you? Just want to kick them. All right. All right, everybody good? All right. So her eggs are formed in the ovary before she's born. Now, they're not mature. She has between 250 to 300,000 eggs per ovary. Don't worry, Linda, you won't use them all. You're not a frog. Okay, you're good. Okay, all right. Meiosis, you could take them through the stages. Some cool things happen in meiosis. So in meiosis, in the first set, now y'all remember it's like doing mitosis twice, okay? But one thing that can happen in meiosis that does not happen in mitosis is sometimes you can get some genes to trade each other out. It's called crossing over. All that does is increase variability. Okay, always remember this about biology, well, about organisms. whether you're a bacteria or you're the highest organism there is, okay, which is supposed to be us. I wish we would behave that well. Really, it's dolphins and whales. They're much more humane than we are. Okay, so variability is the key to survival. Okay, so if you get a question about asexual reproduction versus sexual reproduction, asexual reproduction, I'm glad we don't do it. I mean, I would be horrified if all of a sudden I started to grow another Starla off my side, which is called budding. Okay, and then boop, it fell off and there's another me, identical to me. Then how could you tell which is me, right? Well, but if you're low on the food chain, like really low on the food chain, you're on a lot of people's menus, then asexual reproduction is a good thing because you can make a whole bunch of yourself and survive, because that's the key. If you can't reproduce, you don't get to be around, you become extinct. So the purpose of asexual reproduction is to produce a lot of offspring. The problem with it is there's no variability. So whatever kills one will kill what? All of them. That's right. But if you take half a cell, which is an egg, and a half a cell, which is a sperm, and you bring them together, and it's a brand new combination that's now watch what I'm going to say, because this is important. I love to do this to students, okay? I take an egg, which is 20, for us, 23 chromosomes, and a sperm, 23 chromosomes, and we put it together. That fertilized cell, which is called a zygote. And if you'll just take and you make a dot on your paper, it's about the size of a grain of sand. That's how big a zygote is. That's how big you all started life out as. Okay. Keep in mind, in sexual reproduction, this genetic combination has never occurred before in life, and it will never occur again. It's a great lesson to use with students to show them that you are unique and there is never going to be someone like you. So stick around. Yeah. Okay. All right. So, but in that combining, that is sexual reproduction increases variability. The greater the variability, the greater the chance of survival. For example, what is the kill rate on Ebola? Anybody know? Take a shot. It's okay if you don't know an exact number. Okay, nobody's taking a shot. Okay.
The cure rate is in like how it's
No,
available.
like who's survival rate, like survival rate of Ebola, because you can't treat it. There's no treatment to it. You can take care of them.
0.
No, it's not. It doesn't kill everybody, but somebody said less than 1%. It's actually about, it's got a 93% kill rate. 93, 95. What does that tell you?
Don't
That
catch it.
Yeah, don't catch it. Yeah. But
It's constantly changing.
yeah, and that means that there's people out there that have gotten Ebola and survived. So sexual reproduction makes sure, not just us, but organisms all across the board, that they have a chance at survival, because all of your offspring are not going to be identical. So it might kill off 90% of the offspring, but there'll be that 10 or that 5 or that 1% that what? Still make it. They still live through it. Okay. Look at COVID. Wow, we're still scratching our heads asking, why did this person who was healthy get so sick and had to be on a ventilator? And 8 weeks later, they're going through rehab and they survived, or this healthy person died in 5 days. And this other person who's just as healthy only felt like they had allergies. Well, you all know the answer right there. It's what? Variability, genetic variability. Some systems are more susceptible to a virus attack and others are what? Of course, we're also relating it to gut biome of, how that plays a role in immunity. Okay. All right. Does that make sense? Okay, here we go. Ready? We got to get to the genetic part. So in meiosis, in the last part here, we do not copy the DNA. Okay, we don't copy it. Therefore, at the last part, in anaphase to telophase 2, we're going to take these number 7s and split it. 1, okay. 1 is going to go, they go into an egg, and then the other, of course, is going to go, if it's male, it'll go into a sperm. Okay, so here we go. Ready for the Punnett square? The Punnett square is saying, when this sperm fertilizes this egg, and by the way, this diagram drives me absolutely insane. Okay, and I know some of you are thinking it's a short trip. Okay, okay, watch this. We know that one sperm is going to fertilize the egg, but just kind of give, your students a little bit. The egg has a protective layer around it. It needs 50 sperm, the enzyme off of 50 sperm to get successful fertilization. If you really just had one, it would never fertilize it. Okay, isn't that cool? So the magic number for fertilization in humans is 50. You got to get 50 there, all working together to get through that protective layer. Okay. All right. So we're going to have 1 through 23. So chromosomes 1 through 23, chromosomes 1 through 23. 23rd chromosome is the sex chromosome. The egg is always X. Always. To be a female, you have to be XX. So no matter how you divide it, every cell that's going to form an egg is going to have an X. Does that make sense to everybody? Great. Okay. In the sperm, it's an XY. So 50% of the sperm are going to be X's and 50% are going to be Y's. When we combine here, we're going to make a brand new cell, 46 chromosomes. We'll make it a little boy. Ready? Brand new cell, zygote. 46 chromosomes, XY. I'm using humans, of course. Okay. When they find each other, how did our chromosomes find each other? They matched up. All right, let's do our Punnett square. All right, so what this represents is your chances. Okay, so everybody make your little Punnett square, 4 squares. All right, when we make a protein, when we talked about hair, a protein results in a trait. So that's where a lot of times the flow gets stuck. So it looks choppy. All of a sudden you're talking about the cell and you're doing meiosis with students, or they're doing it, talking about it with you. And then all of a sudden we're in genetics. Okay, key on the word genetics, gene. What's a gene? It's a piece of the DNA molecule that codes for one protein. A protein results in a trait. Okay, so what is genetics? It's the study of traits. It's a study of the section. Okay, so when we're doing this Punnett square, we're focused on one trait. This is known as a monohybrid cross. I'm going to teach you, hopefully I have time, to do a dihybrid cross, and I'm going to show you how to do it so easy. You guys will want to reach through this screen and hug me. You can't until you see me in person. Okay, ready? Monohybrid cross means we are dealing with one trait, just one trait. Okay, let's do some terminology real quick. They like to use guinea pigs a lot, okay, or they'll use flowers or whatever in your crosses. Okay, we could do guinea pigs, okay? We'll do black fur over white fur. Okay, watch this. Let's say that this is our two genes right up here. See, this came from mom, this came from dad. Okay, if both genes, this gene right here, no matter what happens, this animal's going to have black hair no matter what. We call that a dominant gene. Dominant gene means no matter what the other genes are, boom, it's going to mask everything out. It's going to show up. That's a dominant gene. Kind of like a dominant person. You know, it doesn't matter. They can ask you what you want, but really you're going to go eat where they want to eat because they're going to dominate. Okay. All right. Ready? All right. So this gene right here, if it only shows up when both genes are the same, it can only show up if both genes are the same. It's known as a recessive gene. It's kind of like that shy person never says anything. That would be our white fur. White is a recessive gene. So if you've seen people that have along their forehead, they have that widow's peak, that's a dominant gene. I'm looking right now at some of you. Yeah, you don't have that. So we're recessive. Yeah, we're a recessive gene. You've seen earlobes. See, mine may attach directly. That's a recessive gene. You've seen the dominant ones that are separate. Yeah. Cool, huh? All right. Now, okay. So when we do the Punnett square, we're only concentrating on one. All right, ready? So we have to have a key. So here's our key. Black fur. The dominant gene is always capitalized. See it? So usually what they do for dominant is they use the first letter of the dominant trait and they capitalize it. Now, notice I didn't write two of them. See that? I only did this because no matter what this one is, it's still going to result in what? Black fur. Okay. Then we use the lowercase letter for white fur, which is going to be our recessive genes. And remember, for white fur to show up, both of them have to be recessive. All right, is everybody okay so far? I know we could spend probably another couple hours on this. Okay, now watch this. So we have some terms. There's two combinations that will give us black fur. There's where both genes are dominant. And then there's where you have one dominant and one recessive. Both of those will give us black fur, right, everybody? Okay. When both genes are dominant, it is known as homozygous or pure dominant. So homozygous, homo of course meaning same. Homozygous dominant or pure dominant. I'm preparing you for whatever terminology they use on the exam. Okay. All right. Everybody good with that? Okay. If you have one dominant, one recessive, it is known as heterozygous. Hetero meaning opposite. Or you also see the term hybrid. Hybrid mean a combination of the two. Now, just like when we did the fat and we branched out to all different situations, the same thing's going to happen here. Okay, good. Okay, now, I'll be honest with you. Right here, this one, you're going to see the same thing. They'll call it homozygous recessive or pure recessive. But I'll be honest with you, you don't even need those terms. In order for the trait to show up, it just has to be recessive. So again, in your exam, be prepared. If it says homozygous recessive, that's what it is. If it says pure recessive, that's what it is. Or if they just say recessive, you know that's what it is. Because that's the only way that trait, white fur, you're going to get a guinea pig with white fur only if both genes are white. Cool? Now do not relate that to yourself, because humans have to have 12 pairs of genes for skin color and hair color and eye color. So don't pertain that to humans. Okay, is everybody ready? Is everybody cool? Okay, we're going to do this cross. We're going to take the mom, our female guinea pig, who's a hybrid. See her right there? And we're going to cross her with a male that's hybrid. So that's our cross. All right, we have to split her. Okay, now this is, we're going to take it through meiosis. This is when she is in, that's her gene pair. Watch what we're going to do. One gene goes to the top, one side, and the other one goes over here. So see it? I always put the first set on top. That's just kind of my deal. It keeps me organized. So now ready? One egg will get that, and one egg will get that. Cool? Again, genetics or the Punnett square is really all about statistics. It's not about reality. Okay, it's all about what is the chances of. Okay, ready? Then we're going to put the sperm, we're going to make the sperm. One sperm's going to get a dominant and one sperm's going to get a recessive. All right, so put that down the side. Okay, how's everybody? We good? Whew, man, the cobweb's coming off. Okay, here we go. This is simple. So these four represent what are the possibility of your offspring. Okay, what is the predictability, the percentage of what your offspring could be? All right, here we go. Well, this one could be what?
Capital BB.
The pure dominant?
Pure dominant. So put that down. So watch what, to help, dominant genes always get written first. Okay. All right, in this case, that doesn't really matter. So pure dominant. All right, come across here. What do we have here?
Hybrid.
Hybrid?
Hybrid, that's right. And remember, always put the dominant gene first. Okay, go ahead and work the other two out and then see how you do. And is that what you got? Okay, good. Okay, ready? Now, you've done it. We have two things we're going to get from this. First, we need to know genotype. Key on it. Genotype. What sets of genes do we have? All right, let's write them. We always start with the strongest gene pair first, which is going to be pure, then hybrid, then recessive. Now you're going to do your predictabilities. Okay, here we go. Always remember, we go strongest to weakest. Okay, ready? We have 4 squares, right, everybody? Okay, how many of these do you see?
1.
1. So you put 1 over 4. So that means 1 out of 4 boxes is going to be pure dominant. That means you have a 25% chance of having a pure dominant offspring every time fertilization takes place. Okay, all right. How many hybrids do you have?
2.
2. So you put 2 over 4, and then that leaves you with what?
50%.
Yeah, 50% chance you're going to get a hybrid out of these 2. Okay, so now ready? Now remember, this is just the percent every time there's fertilization. There's no guarantee because there's variability, right? All right, so if I ask you in a question, what is the genotype of 2 hybrids? Okay, watch what it is. It is 1, 2, 1. All you do is to name the top number. That's it. 1, 2, 1.
So you're saying the answer for any genotype would be the top number you take it. So this would be
Yep.
1, 2, 1.
Yep, I'm gonna give you a hint. Every time you cross 2 hybrids, regardless of what trait they throw at you, it will always be 1, 2, 1. It doesn't matter what trait they put at you. Anytime you cross 2 hybrids, you get 1, 2, 1. Okay, now we're gonna do the phenotype. The phenotype, guys, is actually, you can always find the phenotype because it's actually going to be your key up here. So whatever key they give you, that's going to be your phenotype. Okay, phenotype, remember this, always remember about phenotype. It's what they look like. It doesn't matter gene pair. The phenotype, ready? Watch the key word. Phenotype, feature. Phenotype is what they look like. So what can this guinea pig look like? Is either what or what?
White or black.
That's it. So we always do dominant color. It doesn't matter what the second gene is. So he's either black or he's going to be white. All right. Now, question. You can go up here and count these if you want, but I'm going to show you an easier trick. Is this black?
Mm-hmm.
1. Is this black? What's 1 plus 2? 3. That's not black. So how many do you have?
3 ones.
You have 3. That's right. 3 out of 4 and 1 out of 4. You could go back up and count it, but I'm setting you up for a cool way to do dihybrid.
So the phenotype is 3-1.
Yep. So 75% chance of getting black offspring. You only have a 25% chance of getting a white guinea pig. So you could mate these 2 and maybe mate them for, well, they don't live a long time, for 2 years, and you get nothing but black offspring. You never get a white offspring, ever. Or you could mate them for 2 years and you get 75% white and 25% black. Remember, this is just chances, which means, wow, you can sell high dollar because this guy right here is rare. You're lucky. Lots of times recessive traits are referred to as weaker traits, but that's not necessarily true. Okay, is everybody cool? Let's do another one. Okay. Cross these. Same trait, everybody. The female is pure black. She's a homozygous dominant. And you're crossing her with a white. Okay. And I want to know the genotype and phenotype. You're being photobombed, Linda. You got somebody stealthy behind you there. That's right. Very good. What's your genotype?
For hybrid.
That's right. So 040 would be your genotype. Okay. What's your phenotype? What are they going to look like?
100% black.
Yeah. So can you ever have a white? Never. There's no chance of ever having a white guinea pig in this combination. So if you cross a black guinea pig that's pure, now let's cross this one. Let's do this cross. Let's take the offspring and cross it with a pure white. Let's see what our chances are. So cross a hybrid and a recessive. Crossing a black hybrid with a white guinea pig. Remember to always put the dominant gene first.
Do we have a 75% chance of having a white one? No. No. Okay.
Would it be a 50%
50-50.
hybrid and then 50% recessive?
So your genotype should be, so double check your work,
022.
022.
I have a little bit of trouble on the phenotype still.
Okay, so remember phenotype is either they're going to be black
Uh-huh.
or they're going to be white. And remember, you can do it like this, black or white, because the second gene doesn't matter. As long as the first gene is dominant, they're
Okay.
black.
Okay, thank you.
So now if you missed it, look where you missed it. Okay. It's okay to make mistakes, just look where you did. Now, the nice thing about genetics, it's a lot like statistics. This is repeated. It doesn't matter what gene it is. You cross two hybrids, you get 1, 2, 1. You cross a hybrid and a recessive, you're going to get 0, 2, 2. You cross a dominant to a recessive, okay, you're going to get 0, 4, 0. I mean, it's repetitive, but if they give you a question like that, go to the side and work it out.
Okay.
Geno, what kind of genes? Pheno, what's it look like? Does it have the trait or is it recessive?
So Starla, my box looks just like yours, but when I get to the Geno, I I'm not picking that part of it up. So
Okay,
I wrote
ready?
a quarter and a quarter, but that obviously was not correct.
No, ready? So always put your gene pair. How many of these do we have? How many pure dominants do we have? None. How many hybrids? You can even go cross them out if you want, cross them out of there. How many recessives? 2.
So is the 0 is nothing. It's not a quarter because it's 0.
Yeah, the 0 means that is not going to occur. That genetic combination will not occur. There's not a
Starla,
chance. Mhm.
But you always have to account for it, right?
Yes,
When you're doing the
always
gene.
have to put it in. So if it's a 0, you still have, because if you just said the genotype was 2-2, 2-2 what? Yeah. So there's 3 genetic combinations, and you always start strong to weak, pure, hybrid, recessive. So if it's a 0, you still, like you said, you have to put a 0 in.
Thank you, because I get it now.
All right, good. Good.
Starla, I know you like to teach clear to the last minute. We've got about 7 minutes left.
Okay. So I don't know if we have time to do a dihybrid with you. I'm not sure if they'll put that on there for you.
Starla.
Yes.
So on my last 2 tests that I've taken, neither one of them used Punnett squares. They had like pedigree. That's what was on.
Okay. Okay. It's the same thing. Yeah, you're doing the same thing with pedigrees. All you're doing is following the dominant trait. Okay. So let's say you're going to buy, you're buying a purebred. They're advertising it as a purebred Mastiff. Okay. Then you breed the stud to another purebred Mastiff, but you get a puppy that has got some different traits in it than a Mastiff. What's that tell you?
Hybrid.
One of those dogs is hybrid.
Mm-hmm.
That's right. That's how we can tell if somebody's lying. Okay. And I'm going to tell you, like in the horse trading industry, as you all know in Oklahoma, or the dairy cows, man, pedigree, genetics, that's a big thing. If you're going to pay $25,000 for this bull, and these are its traits, by God, you better be truthful. Because if I'm going to take the sperm and I'm going to pregnate 10 of my best top dairy, my whatever I'm doing with these cows, I better not see offspring that have traits that don't belong to a purebred. Then I know that stud is not a purebred, it's a hybrid, if it's starting to throw recessive traits. Does that help?
Yeah, I think it's the way they use like the circles and the squares and the different. I think that's what confuses me.
So I was going to show you what those do. Ready? So if I were to do this for you, this is what this would look like. So this is a hybrid, and that's a recessive. Okay. All right. So we started out like this. We started with 2 hybrids, right? Okay. So here we go. This was our first generation. So that was our first, and they'll put a 1. They put P1 for first generations, parents 1, 2 hybrids. Okay. Now here you go. Ready? Now, on a pedigree, guys, they're actually supposed to put what actually happens. Does that make sense? They're supposed to put, this is really what we got, because this is going to be F1, which is going to be the offspring 1. But we're going to put what we got. Okay, we got 1 dominant. We got 2 hybrids. And we got 1 recessive. See how they would write that? but they're supposed to actually put, you're welcome, Deborah, thank you. They actually supposed to write what they actually got. Okay, all right, then we took a dominant. We took this guy right here. We took a dominant and a recessive. And that's just a whole different trait. And then we did this. That would be a different one. So see how they would write it. So see how they're doing it? Yeah. And then so if they combine these two right here, they would bring it down and then they would get offspring on that. And that's just generations that they're showing you. Okay. All right. Does that make sense, everybody? That help? We didn't get to the dihybrid, but like you said, maybe you've not even seen that. You never know. They change it up, but the pedigree is the same thing as basically the punnets. But there's when they do the generations, they're saying, well, this is what we got. Is this parent really pure? Well, it'd be pretty easy to figure out because why? If they're pure, you should throw a recessive. Yeah. So if I said this right here, is he pure? Yeah, it'd be easy because all of the offspring, no matter what, they would be hybrid, but they would still be all black. Whoops, 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 whoops. There you are. There we go. There we go. They would all still be black. Does that make sense? Okay. All right. Any other questions? I'm here. Can I get Starla's website? You can. It's Starla's Teach Tips, all one word, .com. Starla's Teach Tips.com. And the cell one is under Stars Notes, Module 1. There you go. Thank you, Susie.
You're welcome.
And guys, you can put my email up there too. And she's got my email. And feel free to email me questions. All right, if you're running across something and even though our tutorial is over, I'm here for you. I'm a resource for you always. So
Starla, do you want me to put the SU in?
15.
15, okay.
At yahoo.com. And then
Okay.
you guys feel free, if it's tomorrow and you're running across something, like you said, the pedigree, you just email me. This doesn't have to end. I'm happy to help you all the way through so you can be successful.
Hey, I wanted to pop in and say hi, Starla.
Hi, Laura. I hope you're feeling better.
I am. Yeah, I'm feeling okay. I just have to stay at home. So, but did you get what you needed today? I sent y'all a message saying, let us know if this was helpful or if you need one again after you take your test, or were there things that you wish we would have covered? I mean, we might be able to contract again if Starla wants to.
Sure. Anything for you guys.
Or they're asking, will you offer any more classes? And they would do it again.